Have you ever stopped to wonder what really made the first personal computers, well, personal? What was that spark, that one breakthrough that basically set the stage for every powerful machine we use today? Well, a huge piece of that puzzle lies inside the brilliant design of an absolute legend, the Intel 8086 microprocessor.
Hey everyone, and welcome to my YouTube channel. Today we are diving deep into the architecture of the 8086. And to really get why it was such a big deal, we first have to understand the problem it was built to solve.
You see, before the 8086 came along, processors were kind of stuck in this slow, one-track mind loop. They'd go to memory, fetch an instruction, then execute it. And only after it was completely done could it go all the way back and get the next one. It worked, sure, but man, was it inefficient. The 8086 completely changed the game by asking a really simple question: why wait? It figured out how to go grab the next instruction while it was still busy executing the current one.
This amazing idea is called pipelining. And honestly, the best way to picture it is to think of a car factory assembly line, right? The factory doesn't build one entire car from start to finish before even thinking about the next one. No way. Well, one car is getting its wheels put on, another one is getting its engine installed, and a third one is getting painted. It's this constant overlapping flow, and it just makes everything so much faster.
So, quick question for you then. What's the biggest win from this whole assembly line approach? Is it A, B, or C? If you guessed B, you're exactly right. It's all about increasing instruction throughput, just getting way more work done in the same amount of time.
So, how did the 8086 actually pull off this magic trick? Well, it wasn't magic at all, just some seriously brilliant engineering. The designers literally split the processor's brain into two halves and gave each one a very specific job to do.
And here they are, the Bus Interface Unit, or BIU for short, and the Execution Unit, the EU. This whole division of labor idea is the secret sauce behind the 8086's power. One unit handles all the talking to the outside world, while the other just focuses on the number crunching.
Let's start with the Bus Interface Unit. I want you to think of the BIU as the processor's super efficient librarian. Its entire job is to run to the library shelves, which is our memory, and grab the books, which are our instructions and data. It handles all the communication with the outside world.
So as you can see, the BIU is juggling a few key jobs. It's constantly fetching instructions, reading and writing data, and it even keeps a little 6-byte line, or a queue, of upcoming instructions ready to go. But its most clever trick is figuring out the exact 20-bit physical address it needs to find any piece of information in the computer's memory.
Okay, so how does that work? This is so cool. The 8086 had a 20-bit address bus, but its registers were only 16 bits. So to bridge that gap, the BIU does a little math. It takes a 16-bit segment address, shifts it to the left by 4 spots, which is basically like multiplying by 16, and then it adds another 16-bit offset on top of that. And voila, you get a full 20-bit address that can access the entire 1 megabyte of memory. Just a really clever way to solve a hardware problem.
All right, so just to lock that in, what's the BIU's main gig? That's right, it's C. Its primary role is to be the master of fetching instructions and data from memory, making sure that pipeline is always full and ready to go.
Okay, let's move on to the second half of the brain, the Execution Unit, or EU. Now, if the BIU is our librarian running around grabbing books, the EU is the scholar who actually sits down, reads the books, and does all the thinking and processing.
And inside the EU, we find its workspace, the general-purpose registers. Think of these like a scratch pad. You've got registers like AX, the accumulator, which is used for math. BX can hold memory addresses. CX is perfect for counting loops, and DX helps out with trickier stuff like multiplication and division. This is where all the data gets tossed around and manipulated.
The whole workflow inside the EU is this really precise process. First, it grabs an instruction from that queue the BIU filled up. Then, the control unit figures out what the instruction means. The data it needs is pulled from the general registers, and then, bam, the arithmetic logic unit, or ALU, does the actual math. And finally, the flag register keeps notes on the results, like if the answer was 0 or a negative number.
So all that heavy lifting, all that number crunching for things like addition and subtraction, it all happens in one specific place, the arithmetic logic unit. The ALU is the true mathematical core of the entire processor. All right, now for the grand finale. Let's put it all together and see how these two units work in perfect harmony to create that pipelining magic we were talking about at the start.
So picture this. The execution unit is deep in thought. It is completely busy, working hard on executing instruction number 2. Now, in an old processor, the rest of the chip would just be sitting around, waiting, but not in the 8086.
Because at that exact same moment, the bus interface unit is already looking ahead. It's already fetching instruction number 3 from memory and putting it in the queue. So the second the EU finishes with instruction 2, instruction 3 is sitting right there, waiting for it. The EU almost never has to stop and wait for work. This parallel action, this is the soul of pipelining.
And that really brings us to the key takeaway. It was this simple but totally profound idea of splitting the work into two specialized parallel units, one for fetching, one for executing. That's what made the 8086 so much faster, so much more efficient, and what made it a blueprint for generations of processors that came after it. And that kind of leaves us with a final thought, doesn't it? This whole divide and conquer strategy, first pioneered way back in 1978, is more relevant today than ever before. I mean, when you look at the multi-core, hyper-threaded processors in your own computer, you are literally looking at the direct descendants of the 8086's revolutionary idea. How's that for a legacy?